All right, anyone have any questions or need anything before we get started?
How you doing, Dave?
Tired. Weirdly didn't sleep so great last night. I'm not sure why. But I hope you guys slept good. Fair enough. Sleep is weird and ephemeral. So, down to the last week of class. Frankly, kind of feels like less than the last week since they've cut class on Friday. Anyway, our objective for today is to cover one last very small chapter on electricity. I mostly just want to cover the things you'll need for lab this week and the things about electricity that you will most commonly use as potentially non-electricians, which is to say how to calculate and control your electric bill. Again, this will be useful in lab this week, so make sure to bring any notes you record today to lab. Lecture on Wednesday will be focused primarily on wrapping everything up and making sure you guys feel comfortable for the exam, going over materials that I post to study for that.
What are the exams?
The exams for this class are next Monday. I had them written, but I had to erase them for diagrams. $130. I have two sections of Physics 1000, so I have two pre-scheduled time slots for Physics 1000 exams. They are both next Monday, April 29th. The first one is at 8:30 a.m., the second one is at 1:30 p.m. Since I'm giving the same exam twice, I don't really care which one you show up for. Just note that probably more people are going to prefer the 1:30 option, but I'll deal with that when we get to it. So I don't care which one you show up for if your schedule allows for and would benefit you attending the opposite one.
How many points is final work?
The final is 25% of your grade, which is actually the same as each single test. So hypothetically, if you got A's on both tests and did all your labs, you could not take the exam at all and walk away with a C.
Is the exam just in this room?
Yes. Or if the white law's available, I might move us in there. The big auditorium right next door, bio boards. Any other questions for right now? All right. In that case, last little bit of learning, electricity. Now, who knows what electricity is, like physically? It does, yeah. Sorry, it's Monday and I can't talk. Electricity is, at least in part, the motion of energy. Yes, we use electricity to get energy from point A to point B. That's the entire reason that we have built our society around it, is you can generate energy at a power plant and then use electricity to get that energy from the power plant out to everywhere else. So, electricity does transfer energy. That is what it does. Correct. What I would like to know is, do you guys know what the electricity itself is physically comprised of? Because energy isn't matter. Energy isn't a physical thing. It just does physical things. What, in terms of matter and materials, is electricity made of?
Electrons.
Electrons, specifically moving electrons. Very good. Remember from a month or so back, we briefly reviewed the parts of the atom, electrons being the negatively charged part that orbit the actual body of the atom. The electrons are able to leave the atom, and that's why electricity is considered to be their motion, because protons and neutrons are stuck in the nucleus and they can't go anywhere. Electrons can actually travel from point A to point B. They tend to leave the orbit of one atom and jump into the orbital of the next one, so on and so forth, all the way down the chain of its pathway. So electrons can go from point A to point B far more easily than either protons or neutrons can, and so electricity is formed by the motion of electrons. They are the charged particle that can most easily move. So a lightning bolt is physically made of a bunch of electrons all surging from point A to point B very quickly. That is what electricity is physically made of, and if you ever get, heaven forbid, if you were ever electrocuted, what would be physically happening is electrons would be passing through your body from one part of contact to the other part of contact. You can never get shocked if there is only one point of contact, because electricity is the flow of electrons. Their presence doesn't hurt you, them moving through you hurts you. Because as electrons move through something, they carry energy and leave some of it behind. So if you are ever electrocuted, what's happening is electrons travel through you and leave energy inside of you, which cooks you from the inside out, which is, medically speaking, bad. But electricity is physically made of electrons, and that means technically a lightning bolt has mass. If you've ever thought about that, because electrons have mass. You could weigh a lightning bolt if you could keep it still long enough and not die. Now, related question before moving on. Can you see electrons? I certainly can't. So, what are you actually seeing when you see a lightning bolt? It's a good vocab word, but not technically. We will cover that word today, though. Let me first describe what is going to happen leading up to the lightning bolt. These are clouds, very poorly drawn clouds, and this is a very poorly drawn tree. In order to generate lightning, the traditional way, you have a bunch of clouds in the sky, and those clouds all are constantly blowing around, moving past one another, and they will electrically charge themselves via friction. The same friction that you use with wool socks on the floor to generate static buildup. So when these clouds are charged, they have built up more electrons than they're supposed to have, and that's true of anything that builds up a net negative charge. You have more electrons in you than you're supposed to, and when you discharge them, you get rid of them, and that's when you get the zap. Electrons don't want to be anywhere near each other because they're all negatively charged, and negative repels negative. So they're all stuck up here, but they don't want to be together. It's a very hostile roommate situation. And so they're just waiting for an opportunity to leave the cloud, to leave each other's presence. And basically they're just going to drift along until some very tall, relatively positively charged object comes close enough to do the trick. And this is why tall objects tend to get struck by lightning first. The taller the object is and the more positively charged it is, you're going to get more electric force that can finally literally rip all the electrons out of the sky, through the air, into the tree, and into the ground. So electrons will travel from cloud into tree. But they don't just travel through empty space, because we have an atmosphere. They have to travel through air. Electrons can never travel on their own. They always have to jump from one atom to another atom. And so what they're doing is they're jumping out of cloud atoms and then daisy chaining through air molecules until they start passing through the tree's molecules instead. And then they go from the tree into the dirt. What you're actually seeing during a lightning bolt is the air that the electrons are passing through. As I mentioned, and you pointed out, that electricity carries energy from point A to point B. And so when the lightning passes through air, it leaves energy in the air. And when you energize air enough, make it too hot and too electrically charged, it turns into plasma for a split second. And plasma, as you can see in these light bulbs, glows. You can also see it in the sun and neon signs. So when you see a lightning bolt, what you are temporarily looking at is plasma for the brief moment that it lasts. And this is why lightning tends to have the same smell as the ionized particles coming off of old TVs. It's literally ions, ionized air, plasma. I don't know if those TVs are common enough that you guys know what I'm talking about, but I sometimes get the same smell when there's a thunderstorm approaching. If you think you can ever smell a storm coming, what you're smelling is probably charged air ions. So that's what lightning physically is. It's physically made of moving electrons, and the reason you can see it is because it turns the air into plasma, and then it glows for the split second that it's plasma. That's even true of just static charges as well. If you just zap yourself and you can see the light, there was plasma there for a split second. Humans have taken advantage of this in the construction of light bulbs, because most of these types of bulbs, it's just gas in a tube that you run current through, and it glows at a particular frequency. Neon signs are the same. They just use specific types of gas to create different colors of light. That all sound good so far? All right. I like all this stuff, and I like space, so I want to ramble for a second. Different stars create different colors of light based on what types of gas they are made of as well. So if one of them is twinkling more red, if one of them is twinkling more blue, it's because they're made of different stuff. And different sizes and different temperatures. I find it all very interesting. When humans take advantage of electricity, we tend to do it through circuits. We intentionally build a system that has electricity flowing through it so that we can have energy going from point A to point B. Because that is the thing we use electricity for, is the transportation of energy. And when we build a circuit, there are three main parts to a circuit to the use and flow of electricity in modern science. Those three parts, summarized in this formula here, which we will be using and explaining, those three things are current, the rate of flowing electric charge; voltage, the electric pressure that drives the current; and resistance, measure of how hard it is for current to travel through a particular object. I'll be explaining each of these one at a time. Questions for right now? Would you guys rather I hang out here so you can copy things down for a second? All right. First up, I want to talk about electric current, because this is what the electricity actually is. This is the measurement of the electricity. Current, the definition of electric current is the amount of flowing charges per unit time. This formula here says I, which is current for reasons that have not been adequately explained to me. I is current. Current is equal to flowing charge, change in charge over time. Q, capital Q, is the unit for electric charge. You're not going to need this formula for anything. I just like to demonstrate that it is flowing charge over time. That is the definition of current. You get current when you have a bunch of electrons flowing from point A to point B over time. And the current, I guess the current amount of current, is the amount of charges flowing through something every second at that current time. I'm using the word current a lot. Thank you. And so the measure of current is the electricity itself. The more current you have, the more electrons are flowing through something. That is the electricity itself. So if there was one measurement, one thing to measure to tell you how much electricity is currently in a situation, it would be current. And current in physics is measured in units of amperes, which is most commonly shortened to just amps. That unit sound familiar? All right. So amps measures electricity itself. And I pretty commonly compare electricity to water because they both flow, and there's a lot of other similar things besides that. Electric current is similar to just water current, the flow of water. Current always travels from one place to another, and the amount of current is how much stuff is traveling per unit time. More current means more stuff per unit time. So a high amount of water current would be physically a lot of gallons of water zooming past every second. A very small amount of water current would be, maybe a water bottle's worth of water every second. Same with electricity. The more amps, the more electrons travel through something every single second. So the amps is the electricity itself, and that's why this is the most dangerous part of electricity itself. Amps kill you. If you, again, I'm going into a lot of ifs, but for safety's sake, if you were ever getting shocked, amps are the part that can damage you. Because the amps is the electricity, the amps is the amount of electrons traveling through you. And the more electrons that travel through you, the more energy they leave behind, and the more you get slowly roasted from the inside out. Which, again, bad. For context's sake, 1 amp, just, the base standard unit of 1 amp, that will kill you if you're exposed to it for about a second. Especially if it's traveling through one of your 2 most vital organs. 1 amp will kill you dead. And for that reason, most commonly used devices and appliances use some number of milliamps, 1,000 times less. Phones, for instance, probably about somewhere between 2 to 10 milliamps. So that, if you did get zapped, it wouldn't be enough to meaningfully hurt you. Any devices that actually use like some number of amps, they do that because they need to, and those are the machines that have fences and yellow safety tape and rubber coating all over everything in industrial settings for the most part. So just safety precaution, amps are dangerous. If you see a sign that says 10,000 amps, run. Is that clear? Sound good? All right. Now, I'm going to start hand waving at this circuit diagram that I've got over here. This is very simple and very typical of just normal circuitry imagery that you will see in, electricity textbooks. Within this diagram, the current is what you're going to have flowing through the circuit, carrying energy from one thing to another. And in order to have current flowing in a circuit, you need wires, an unbroken connection from the origin of the current all the way back to that source. So to kind of mention what each of these symbols mean, this is the battery, and you need a wire connecting one end of the battery all the way to whatever it is you're powering, out of whatever it is you're powering, and back to the other end of the battery. You need an uninterrupted connection for current to flow all the way around. Circuits have to go in circles like that. And that's why you should never get electrocuted if you only have one point of contact with whatever you're touching. Problem is, your feet tend to be on the ground, and that's a second point of contact. And current can go, from here down your arm and out your feet. But that's why you might have heard safety advice where if your car is ever struck by lightning, don't leave it, because you want to make sure to not touch the metal of the car. As long as you are not forming a closed circuit with any part of the car in the ground, current can't flow through you. So now, moving on from current, we're going to talk about voltage, which is the thing that causes the current. I said I compared electric current to water flow. I'm now going to compare voltage to water pressure. In order to get water to flow, you need pressure to physically push it from point A to point B, and that is the role that voltage serves in a circuit. To compare back to the lightning cloud from a second ago, when there's a bunch of electrons built up in here, there is a large amount of voltage, of electric potential and force that wants to push all those electrons out of that cloud. And electrons are always going to travel from high voltage down to low voltage. And that is what determines what gets shocked. The closest low voltage source in comparison to the high voltage charge of the cloud. This is again why lightning tends to strike tall things and metal things. So don't be a phone tower and don't golf in the lightning. So the voltage is the pressure that causes the electrons to actually start flowing. In terms of this circuit diagram, the voltage is supplied by the battery or the wall outlet. And that's usually why when you look up the electricity of a wall outlet, you might be told American wall outlets use 20 volts, because what the outlet is providing is voltage to get the electrons in your machine to start flowing. So what the battery here is doing is, it's the voltage source, it's what causes the pressure to get electrons to flow from one end of the battery through the circuit and back to its other side to reset. And voltage is measured rather conveniently in volts. It's one of the few units I feel that makes any sense. So capital V for voltage, capital V for volts, not to be confused with capital V for volume or lowercase v for velocity. It's still a flawed system. Now, high voltage is not as immediately dangerous as high current. High current is inherently dangerous because current is what kills you. High voltage has the potential to kill you. But if you had like a 10,000 volt battery sitting on the floor, it's not going to do anything unless you're touching both ends of the battery. It has the potential to output lots of current, but that's it. How much current it actually outputs depends on what it's connected to, and it has to be connected in order to do it. Voltage can create the thing that kills you. Current is the thing that kills you. So a sign that says warning 10,000 volts, don't touch anything. A sign that says 10,000 amps, leave. Because if the amps are currently flowing, you don't want to be the thing they're flowing into. Does that make sense? Okay. So voltage causes current current. Voltage pushes current to flow through your circuit. The last piece of the circuit is what is the current flowing through? And you can connect anything into a circuit. This squiggly line here could be anything. The straight lines are wires, the arrows are current flow, and this squiggly line here is something that's been plugged into the circuit. And that could be anything. It could just be a piece, like physically a little circuitry piece. It could be your phone charging brick. Anything that you plug into a circuit becomes a part of the circuit diagram and acts as a resistor in the circuit. Electrically speaking, a resistor is anything that resists electricity flowing through it. And secretly, everything resists electricity flowing through it. It's just a matter of how much it resists electricity flowing through it. You may be familiar with how metal and water allow electricity to flow through them very easily, which is, again, why you don't go golfing in a storm and why you don't go swimming in a storm. Conversely, you might have also heard that rubber does not allow electricity to flow through it very easily, and that's why we tend to coat most of our wires in rubber or plastic. Sound familiar? That is because those two different materials have, well, several different materials, have different resistances. We measure resistance in a unit called ohms. That unit is spelled H-O-M. Sorry, I said that wrong. O-H-M, ohm. And I don't actually have it on the notes, apologies. The unit for ohms, the actual symbol, is Greek omega, the horseshoe. So if you ever are looking at an electrical diagram and you see this, that is referring to the resistance of that thing. Low resistance, low ohms, low omegas, means that it's very easy for current to flow through that particular object, and therefore a lot of current is likely going to try to flow through it. A very high resistance, high amount of ohms, means it's very hard to push electricity through that thing, and therefore electricity is not going to want to be pushed through that thing. You would require a lot of voltage in order to get current through that thing, and even then the current's not going to be happy about it. Because current always it prefers paths of least resistance. More on that later. Whatever you plug into a circuit acts as a resistor. It resists the flow of electricity through it. And since it's resisting the flow, it's taking energy away from the flow of current. Everything the electrons have to pass through sucks out some of the energy of the electrons. And the bigger the resistance of the resistor, the more energy it siphons from the current flow. So the higher the resistance, the more energy it absorbs from the current. On the one hand, that means it's harder to push electric current through things like rubber and plastic and glass. On the other hand, it means that if you do push current through them, they're likely to start overheating very fast. Because if they're taking a lot of energy out of the current, now that material has the energy in the form of heat. And that's why your laptop might melt itself if you overuse it. Literally, it's building up heat because of basically electrical friction, which is a thing. But you need a resistor in the circuit because the resistor is what you're trying to power. That resistor, that squiggly line, could be a light bulb, it could be your phone brick, it could be literally anything. If you are powering something with this circuit, it is acting as a resistor in it. And the bigger its resistance, the more energy it draws out of the circuit. And the harder it makes current to flow through it as a whole. And so those are the three things that you need to build a circuit. The voltage source, the wires for the current to flow through, and then the thing that you're trying to get the current to flow through acting as a resistor. Does that all sound all right so far? All right. Now this is the part for lab this week. This formula here, Ohm's law, tells you the relationship between these three things in a circuit. Basically, the voltage has to push the current through the resistor, and this is the relationship between all those numbers. to demonstrate, you are setting up a lab that requires 2.5 amps of current. That is the amount of current that needs to run through this system in order for everything to get powered, which is a lot. You know, that will kill you in less than a second, so safety gloves. We need 2.5 amps of current, and we have access to a 100 volt battery. It's about a car battery, I think, or maybe a couple of car batteries, I'm not sure. This is the voltage source we have access to, and this is the amount of amps we need traveling through that system. In order to get 2.5 amps out of that battery, we have to connect it to a circuit that only has a certain resistance to it. The more resistance our circuit has, the harder it is to get current out of the battery. The lower the resistance of the circuit, the more current we will draw out of the battery. So if we want to specifically get 2.5 amps out of a 100 volt battery, what is the resistance requirement of this circuit using this formula? 40. Very good. V equals IR. Therefore, 100 equals 2.5 times R. Divide both sides by 2.5. And R is 40 ohms. If we want to get 2.5 amps out of that battery, we need, at maximum, a 40 ohm resistance system. If our resistance is any higher than 40 ohms, we're not going to get 2.5 amps out of that battery. Which is probably for the best, because 2.5 amps might kill you if you look at it the wrong way. There's way too much current for any system that humans should have to interact with. But that's how you determine how you want to build your system. You figure out how much current your system needs, compare it to the voltage you have access to, figure out what resistance the system can have to pull that amount of current out of the battery. Does that sound all right? Okay. Quick related question. Let's say we have the same 1,000 volt battery, but our equipment instead has a resistance of 80 ohms. Double that resistance. So same formula, but 100 volt battery, unknown current, 80 ohm resistance. If you use the same battery, but the resistance is bigger, you get less current. We would divide 100 by 80, and we would get 1.25 amps. If you increase resistance, you decrease current. This is again why safety equipment, electrically speaking, is always covered in rubber. Because electricity always travels the path of least resistance. If you want to avoid getting electrocuted, 1, coat anything that could be charged in rubber. 2, make sure that there is another path that is more preferable for the current to flow through. The reason that coating wires in rubber works, like there could be 2.5 amps of current running through this wire, which again, will kill me, but as long as the wire is coated in enough rubber, I could grab this and be fine, because the current would have a more preferable path to flow down. Electricity likes the path of least resistance. So if this wire has a resistance of 40 ohms, which is really low, I might add. 40 ohms is an incredibly low electrical resistance. The human body's resistance is like 10,000 ohms. No, it's probably more than that. I haven't checked in a while. But the resistance of the human body is kind of high on purpose because you don't want to get zapped. Most machines have an internal resistance of several thousand ohms at minimum. Again, just for scale. So if this wire's resistance is like 40, and the rubber coating the wire's resistance is, several million ohms, the current's all going to want to go through the wire, because that is the path of least resistance. I could grab the wire, completing a circuit between the wire and my feet to the ground, but it's not going to choose to flow through me because that's just the way too hard option. None of it's going to want to diverge, to force its way through the rubber and into my hand if the metal wire with the incredibly low resistance is an option instead. And humans are very good at taking advantage of this to avoid getting electrocuted. We build things to make sure that getting shocked doesn't happen because we try to provide other pathways that are more appealing to the electricity. That is usually the point of a grounding wire. It's to make sure that the current has if something goes wrong in the system, the grounding wire physically gives the electricity the option to just jump straight into the earth, which is low resistance and a very appealing place for electricity to go. Electricity is constantly trying to go into the earth. That's why it strikes trees, to go through the tree into the dirt. So, use this to your advantage to avoid getting electrocuted. Now real quick, if you somehow know it's inevitable that you will get electrocuted, if you know that lightning is about to hit you and you have like 1 second to react, you can use path of least resistance to save your life. Because there's two parts of your body that you really don't want current flowing through, brain and heart. Those are the two things that keep you alive the most. And so if you know that you're about to get shocked, you want to make sure that the path of least resistance through your body doesn't involve either of those 2 points. So if you are about to get struck by lightning and you can't change that fact, what you want to do is raise your right hand and make sure that your right foot is the only one touching the ground. Because then the path of least resistance from lightning to earth is through your hand, down this side of your body, and out the right leg. Again, this is like last emergency situation. But then the path of least resistance from entry to earth doesn't go through your brain or your heart. Does that make sense? You don't want the top of your head to get hit. You'd rather your hand get hit instead. You also don't want current to go from one hand to the other, because then it goes through several organs. So, path of least resistance, we use it to avoid getting shocked. It's also how birds can stand on telephone lines and not get shocked. It's easier for the electricity to go through the wire rather than try to force its way up through the wire and through the bird. Does that all sound good? Okay. Now all of that information is stuff for lab this week. The last thing I want to talk about is what might be a slightly more practical application if you're not planning on majoring in science, or not majoring in anything that involves electricity. And that is how to calculate your electric bills. In the United States, or I think globally, your electricity bill is calculated based on the amount of energy that you use. And the amount of energy that your home uses depends on the power, on the wattage of all the stuff you've got plugged in. And when I say power and wattage, I'm referring to the same power and the same watts that we used months ago when we were talking about work. Power is work over time, energy used over time, measured in watts, joules per second, same thing. If you know the wattage of one of your appliances, say for example a 60-watt light bulb, that tells you how much energy that bulb needs to be on every second. A 60-watt bulb needs 60 joules of energy every second. And if it gets less than that, it starts dimming until it goes out. And that is what ends up affecting how much energy your house uses, and therefore how much you get billed for at the end of the month. So in general, first tip, try to have lower wattage devices. Because the higher the wattage, the more energy it draws every second, and that's what you get billed for. Thankfully, most bulbs these days are about 20 to 30 watts, so that's savings already. This is a very old light bulb. Bless you. to calculate something's wattage, there's a few formulas here to be able to do that. The power rating of a circuit is going to be equal to the current that flows through it times the voltage that is currently applied to it. So current times the battery. And all these formulas tell you the same thing. They're just using substitutions based on Ohm's law to change what thing you need to put into the formula. They all say the same thing. But the power of a circuit is its current times its voltage. And once you have that power rating, you can use it to figure out electric bills. For example, going back to this question for a second, the lab that we were building, we had a 100 volt battery with 2.5 amps of current coming out of it. So that's V and that's I. The power requirement of that circuit, P equals IV, 2.5 amps of current, 100 volt voltage. This circuit has a 250 watt requirement. It needs 250 joules of energy flowing through it every single second, or the machinery cuts off. That is probably about the energy requirement of 2, maybe 3 laptops. Most laptops are about 100 watts, I think. And the wattage should be somewhere, either on the thing or somewhere in the information that it came with. Now this one doesn't list a wattage, but it does list voltage and current, so I can find the wattage. And once you know that wattage, that's the first step to determining electric bills. To go through how that works, different example, we're going to take that 60 watt light bulb I mentioned, and we're going to leave it on for 7 hours a night. And we're going to figure out how many cents that costs per day. Now, has anyone here ever looked at an electrical bill before? If you have you seen the variable kilowatt hours before? Because at least in the United States, this is the unit of energy that you get billed for. And it is an energy unit. Kilowatt hours measures energy like how joules does. They're just different units for the same thing. And in the US, every different electrical provider will bill you a certain number of cents per kilowatt hour of energy used up. Once you know this rate, and once you know the wattage of your appliances, you can figure out how much they're going to run you based on how long you leave them on. To do that in this case, we've just got one light bulb. A 60 watt bulb that's on for 7 hours a night. To figure out how many kilowatt hours of energy that bulb uses, you literally just take its wattage and multiply it by the hours that it's on. And that's how you get the energy unit of kilowatt hours. How many kilowatts is 60 watts? One more. 0.06. So 60 watts converted to kilowatts is 0.06. So that's the kilowattage of that light bulb. And to determine how many kilowatt hours of energy it uses, you take the kilowatts and you simply multiply it by the hours that it is plugged in and turned on. So if that's 7 hours a night, that's 0.06 times 7. Therefore, this light bulb will use up 0.42 kilowatt hours of energy every night. So that is how much energy this light bulb is using. If you look on your bill or the internet to figure out how many cents per kilowatt hour your provider will bill you, you can then figure out how much money this costs. 0.42 kilowatt hours, 10 cents per 1 kilowatt hour. This bulb will run us 4.2 cents a night. And that is a night if it's on for 7 hours. Per month, assuming a month is 30 days, that is 128 cents which is $1.26. And that's the basics of figuring out what any particular device costs you. Again, as long as you know its wattage, the hours it is plugged in and turned on, and your area's cents per kilowatt hour. Now I'll say again, that's an old light bulb. Most bulbs these days are 20 watts. So let me run through that again. But electricity these days is a little bit more expensive since I wrote this the first time. So modern times, a 20 watt light bulb for 13 cents per kilowatt hour would run you 182 cents. Nope, 1.82 cents per night, which is half $1 per month. All that to say, this is how you can figure out what any given thing is costing you, and your light bulbs are not going to be what is costing you the most. If they're all 20 watts and you've got them on a couple hours per day and night, that's going to run you like maybe $1 per 2 light bulbs per month. So when you get to the point where you're working on your own electrical bills, your biggest users are the high wattage appliances that are on all day, which is usually your fridge and your air conditioner. So just tips for the future. And tips for the take-home lab, the remote lab, the makeup lab, if you do that this week. That's one of the things on there. So, how you guys feel? Any questions or things on your mind for right now? All right, well, that's pretty much it. That's the last new thing I have for you this semester. So, bring these notes to lab this week. There is no whole lab this week. Wednesday, we will wrap up and summarize and make sure everyone's feeling good before the exam. And please have one. It is optional, yes. It'll either fill in a missing lab grade or it's extra credit if you don't have a missing lab grade.
How much? Thank you. Have a good day.